Hi, this is my video number 9 on line integral. Okay, so in xy plane, a curve, in xy plane, any curve, you may express this as a parametric system. X equal to xt, y equal to yt, a parametric system where t is a parameter. Now let me give a brief definition on the curve. We say the curve is a closed curve, closed curve. If x t plus t naught is equal to xt and y t plus t naught equal to yt. So what does this mean? So it means that if you have a curve, so here at t, after some point t naught, you come back to that. So this is x plus t plus t naught there. So it's overlap. So in this case we call it as a closed curve. And a closed curve, we say simple closed curve. If the closed curve does not intersect itself. Okay, for example, simple closed curve is the closed curve that does not intersect itself. So it means that if you have a curve like this is not simple closed curve. Simple closed curve is something like that. This is simple closed curve. Anything that does not intersect, we call it as a simple closed curve. Example of line integral. Example of curve. Example of simple closed curve. We may have x equal to a cos t, y equal to a sin t. This is a circle. Of radius a. So now what do we mean by line integral? What do we mean by line integral? Line integral is the integral that we need to evaluate the integral along the curve C. For example, we want to integrate the integral of function f xy dx along curve C. What is C? C is given simple closed curve. What kind of closed curve is given specifically as a function x equal to what, y equal to what? Okay, or we may have fxy dy, or we may have fxy dx plus xy dy. Okay, all this type of integral is a line integral. Now I give you an example. Let's say we want to evaluate from point 10 to negative 10, a function x cubed minus y cubed dy through a semicircle y 1 minus x squared. So now what is our C? Look at this. If you know, this is the if you square both sides, we have y squared is plus x squared equal to 1. This is a circle, and we take square root. Y is square root those things. It's supposed to be plus minus, but we consider only positive, so it means positive part. So this is a semicircle of radius 1. Okay, so if you look at the limit given here, is 10 to negative 10. 10 is here. This is 10. This is negative 10. Along that curve, so means from that into that. This is the direction of the integration. So this is our C. Okay. So for a circle, the best representation is using the polar coordinates. So in order to solve this, we take x equal to, this is a radius 1, so we get x equal to cos t, y equal to sin t. Right? Then we know from that this is a half circle, so our t should be from what? From 0 to pi, because this is half circle. If 2 pi, then is full circle. Okay, so now if you integrate that, those t from 0 to pi, here you have x cubed cos cube minus sin cube t dy. You need to differentiate this. So dy is cos t dt. So substitute into that. So we have cos t dt. Okay. So I think you can evaluate this. Okay, so probably the best thing you can do is 0 to pi. So we have cos 40. Here you got sin cube t cos t dt. Yeah, to integrate that, integrate 0 to pi cos 40 dt minus integrate 0 to pi sin 3 t cos t dt. I won't solve this in detail, just give you a brief idea how to do it. Here you can use half angle. Yeah, what do we have here? I think cos squared t, this is equal to half 1 minus cos 2t. Alright, don't do this. Yeah, don't do this. Don't integrate cos 40 dt give you 1 over 5 sin 5t. This is wrong. Don't do it. Okay, with half angle You have 4, so you use twice here, then twice, and do it again. You have to do twice. You have to use this formulation twice. For this part, I think the best is using substitution. Substitution, I guess. Substitution. That's the best you can do. So you can take let's say u sine t, du you have cos t dt. Then you can substitute there. You can put the appropriate limit for u. Sine, u is sine, so you have u cube. Cos dt is du. Then you can evaluate this easily. Okay, remember the limit of integration suitably for u. It's not for t. T 0 to pi. Okay, I give you another example. The rest you can do, so I just leave it, this part to you. I'll give you another example. Let's say we want to evaluate this integral. This curve, small circle there for closed curve, which means C is a closed curve. Okay, so we want to evaluate this 2xy minus x squared dx plus x plus y squared dy. Where your C is given as y squared and x y squared from 0, 0 to 1, 1. Okay, so you may sketch the those curve C. Do a little bit sketching to give you idea what does it look like. Okay, so y squared is something like that. X equal to y squared is something like that. So this is x equal to y squared. This is y equal to x squared. So this is your C. So we use counterclockwise direction. If not mentioned, then always use counterclockwise direction. This, if you solve those equations, you have this is 1, this is 1. Now, for C closed curve with what we call this is a piecewise smooth curve. Piecewise smooth because we have one curve smooth, two curve smooth. Alright, it's not smooth everything because here it's not smooth. So in this case, we split that into two. So for the case C, combination of couple of smooth curve, the integral that is equal to C1 plus C2 plus as many curve that we have. Okay, so the same thing in this case. Our C is not smooth, so we split into two. Now let's say this is C1, let's say this is T2. Now to consider C1, for C1, we want to evaluate, which means we want to evaluate this, along C1, So for C1, what we have? We have x equal to y squared So the best thing to do this is, C1 is y equal to x, y equal to x squared. The best thing to do is, we introduce a parameter, let's say a parameter t. So you can choose any of this to be t. For me, I prefer x to be t. If you choose y to be t, then you have to express x in terms of t. You have square root. It's not as easy as that, right? So we use x equal to t. So if x equal to t, so we have y equal to t squared. What about the limit for t? You can choose since s equal to t, and x from 0 to 1, so which means our t also from 0 to 1, because x equal to t. Okay, now you can substitute. If you look at our integral here, okay, we have x, we have y, we have x, and so on and so forth. Now x, y, we can use here x, y. We can substitute just into that, and we also need dx, dy. Okay, so which means here you need to differentiate this. Okay, differentiate that. Yeah, this is dx equal to dt, dy equal to t dt. Then you can substitute everything. So those integral become, for C1, okay, 2xy, x is t, y t squared, so we have 2t squared, dx is dt, plus we have x is t, plus y squared, t squared is t4, dy is 2t dt. So now you can see the integrand of respect to t, no more xy. So here we have t from 0 to 1, here we have 2t cubed, here you have 2t squared plus 2t 5. Alright, so to all those two you can factor out, so just remove this, you factor out, and dt. Again, you can evaluate this. I just leave it to you, whatever value. Okay, let's say this value, let's call this value a. Evaluate this, find what a is. Now you need to consider for C2. You need to evaluate along C2 we have, look at those, our integral. C2 is x equal to y squared. Okay, C2 we have x equal to y squared. So in this case, I will let y equal to t. Okay, y equal to t. So I can write x in terms of y. So x equal to in terms of y. So we have x equal to t squared. Much easier. If you choose x equal to t, then you have to write y in terms of equal to square root t. The square root is not good, basically. It doesn't mean you cannot do it, but I think this is much easier. Now, what about the limit? Look at our diagram again. Y, because we take y equal to t, so you need to consider y. Y from 1 to 0. Okay, look at this. Y, 1 from 0 to y. 1 to 0, not 0 to y. Look at the arrow of the choice of direction that we chose earlier. Okay, so y from 1 to 0. So y from 1 to 0, which means our t from 1 to 0. Okay, Now you can evaluate. Substitute everything. C2, alright, C2 inside the 2xy. Our x is t squared, y is t. So we have t squared, t dx. We need dx. So what is dx? dy equal to dt. dx equal to 2t dt. So here we need 2t dt plus x. Your x is t squared plus y squared is t squared. dy is dt. Then simplify this. C2 t from 1 to 0, t from 1 to 0. Here you have 2 to 4 t4, so 44, right? Here you have 2t2 dt. So again you can evaluate this. So let's call this as a b. Okay, so therefore integrate those function over c is equal to whatever function here, the function that we are looking for. This is equal to c1 plus integrate c2. Okay, this is equal to a plus b, where a you evaluate, b you evaluate, so you can find the solution. Okay, I wish I could give you some exercise to get familiar with. Can you evaluate this integral? I give you this exercise. You can do it if you want. You can leave it if you don't want. That, say y squared dx plus x cubed dy. Okay, and this c, where c is a rectangle, with vertices. We have 0, 0, 2, 0, 2, 2, 0, 2. Okay, so if you sketch that a little bit, so what we have 0, 0, 2, 0, let's say here is 2, 2, 2 somewhere here, that's 2, 2, and 0, 2. Yeah, 0, 2. So we have that circle. Sorry, we have that rectangle. So we have piecewise smooth curve. Piecewise smooth. So consider each of these curve. Let's call this C1, let's call that C2, let's call this C3, let's call this C4. And then consider each of these curve or line or curve, substitute into there, choose the appropriate parameter, then you can solve it. I think that's all for now. Next, I'm going to in the next video I'll talk on green theorem. Okay, bye bye.